Alright, so it has been 3 months since the last video where I said I'd release the next video on the series in a week. So here it goes. Let's dive into IAM roles for service accounts. Right, so the name IAM roles for service accounts, or I'm going to call it IRSA from now on, that name doesn't add anything to the meaning or the approach of that design. So we are going to need to dig a little deep into what IRSA is to understand how to implement it. And unlike the last video, I'm going to directly talk about the architecture before actually doing a demo, because in IRSA you have to know why and how things are done to actually implement it. The complexity of the architecture is not really hidden from the user. If you remember from my last video, one of the key attractive things that I mentioned about EKS pod identities is that it manages to hide the complexity of the underlying architecture from the user. So as a developer or a DevOps engineer who's trying to implement EKS pod identities, you don't really need to understand how it works under the hood to actually get an effective deployment done. But in IRSA, you have to actually know how things are done and why those things are done. A side note, IRSA was actually the predecessor for EKS pod identities. Before EKS pod identities was introduced last year, IRSA was the only approach you could take in an AWS deployment for this problem, which is how to authenticate from a Kubernetes workload into AWS. So you could be asking, if we have a better approach right now as EKS pod identities, why do we still need to talk about IRSA? Well, the answer is simple, because we can't use EKS pod identities outside of EKS. And even in EKS, you can only use pod identities in specific types of clusters. So if you have any other type of cluster that, let's say, resides outside of AWS but still needs access into AWS, then IRSA might be the only approach that you could use. Alright, so this is me at edit time. After editing all of the videos together, I ended up with more than 40 minutes of actual content. So I'm going to split this video into multiple parts, because no one is going to sit through 40 minutes of a deep dive into IRSA in Kubernetes, which, let's be honest, is a super obscure topic. So if you're watching this video to implement an IRSA deployment by yourself, make sure to follow all the videos, because each video covers a single step in the workflow that I'm going to describe. So let's get back to the video. So let's get into some details. Now, in a single sentence, IRSA is about getting access into AWS as federated IAM principles. So if we break that down into more manageable pieces, one of the key components in the IRSA architecture is going to be JSON Web Tokens, or JWTs. Now, I talked about self-contained tokens, or JWTs, in the last video as well. That was going to be helpful if you wanted to implement more granular access policies for EKS pod identities. But in IRSA, JWTs are going to be the key artifacts that are going to facilitate the bridge between Kubernetes and AWS. Now, what happens at the core of this interaction is the workload in Kubernetes that needs to access an AWS service will present a JWT to AWS for it to be verified as a federated IAM principle. Now, this JWT, or the JSON Web Token, will have to be issued by a party that AWS already trusts. So this becomes a problem where we have to establish that trust between AWS and the party that issues the Kubernetes service account token. In AWS IAM, there's a feature called Federated Identity Providers. Now, this is different from IAM Identity Center Federated IAM Providers, which is cleverly named because you can't really understand any of these names that AWS keeps adding to their services. But in any case, we are going to use that feature to establish trust between AWS and Kubernetes, where Kubernetes would be this external identity provider. After that trust is established, then it's a matter of mapping service accounts into IAM roles and establishing granular access where needed. So we can break these high-level steps into further details. Step number 1 would be to establish trust between AWS and Kubernetes, where Kubernetes would be an OIDC compliant identity provider. And step 2 would be configuring Kubernetes, where anytime a service account that is mapped to an IAM role is used on a pod, that pod is injected with proper environment variables. And the last step, step 3, being mapping the actual service account into IAM roles. So after this is done, the workload that is running on the pod will provide that token into AWS. And since AWS trusts the issuer of that token, the workload running in the pod will be given access into AWS, and it will be able to assume a certain role and perform the actions granted by the permissions on that role. So let's go through these steps one by one, because each of these steps have their own little details that we need to worry about. So let's get down into the details. Alright, so the first step in our workflow is to establish the trust between Kubernetes and AWS. For this, we are going to use the feature Federated Identity Providers in IAM. Now, in a typical scenario, this would be a fully fledged SAML or OIDC compliant identity provider, where endpoints from that identity provider will be used by AWS to first discover the identity provider information and second, verify the tokens issued by that identity provider. In most cases, this requires a full implementation of either SAML or OIDC specifications. But in our case, Kubernetes does not implement the OIDC spec fully. So we are going to have to pretend that Kubernetes is an OIDC compliant identity provider and kind of trick AWS into working with Kubernetes for those two scenarios: discovery of the identity provider details and also verifying the tokens issued by the identity provider. These two endpoints are available at the Kubernetes API URL, and any party that needs to read this information needs to hit the Kubernetes API. But in most cases, Kubernetes API URL is not publicly available for something like AWS IAM backend services to hit it directly. So if you are running a Kubernetes cluster, let's say outside of AWS, chances are that you have your Kubernetes API URL secured behind an internal firewall. So there is no direct way for us to specify the Kubernetes API URL as the service discovery URL for OIDC implementation when we register Kubernetes as an external IDP. So the workaround in this case would be to extract that information from Kubernetes and host it somewhere else. But at the same time, we have to ensure that we are generating the correct information and then providing that at the correct place. One approach for this problem is to use an S3 bucket where we would extract the OIDC discovery specification details and the signing keys from the Kubernetes API and then storing them in this S3 location where we'd be using it as an HTTP endpoint. When we do this, we need to make sure that we are changing details in the API server so that the tokens issued by the API server also reflect the correct details that point to this S3 bucket. You can use a dedicated bucket for this specific case, or you could use a single bucket for multiple Kubernetes clusters that you would have in the future. I'm going to go with the second approach where I already have a bucket that I could use for such a scenario. For this scenario, I have a local kind cluster running without any workloads at the moment. So if I list the pods, you can see that I only have the Kube API server and other control plane pods running on this cluster. The first step of our workflow was to create an S3 bucket so we could extract the OIDC details and store that in the bucket. The second step would be to configure the API server so that it would output the correct OIDC details after we would make this change. So for that, we need to edit some of the details in the API server so that it would output the correct details when we hit those URLs, those well-known URLs, and also so that it would generate correct service account tokens for AWS to verify using the details that we would have in the S3 bucket. For an example, the current information that I have on the endpoint are like this. So you can see that the issuer URL here is pointing to the default value that you would get in a typical Kubernetes cluster, and also the signing key URL here points to an internal IP which will not work with an AWS deployment. So we have to change details like this at the first place, and also we have to make sure the tokens issued by API server also reflect correct details for fields such as issuer claim in the JSON Web Token. To do this, I'm going to make sure 4 flags in the API server configuration reflect the changes I need. So for that, I'm going to go into the control plane. Typically in a KubeADM configured cluster, these static pods or the control plane pods that are started as static pods, the configuration for those pods are in the manifests folder. And in a usual scenario, these manifests are inside etc Kubernetes manifests. If you have a custom Kubernetes setup, make sure that you find the correct manifest folder path because you have to make sure that you are editing the correct details. The first flag that I'm going to check is called the service account issuer. This is the URL that we saw in the discovery spec that we received from the Kubernetes API. And this will be the value that will be used in a service account token as the issuer claim. You could specify this flag multiple times, but in my case, I'm just going to replace this whole value. Now this value should be the base domain or the base path for the OIDC discovery specification. So remember that we are going to offset this information from the Kubernetes cluster into an S3 bucket. So the correct URL should be the URL of the S3 bucket. So in my case, I'm going to use the S3 bucket URL and a subpath inside the S3 bucket. And for this subpath, I'm going to use the first 8 characters of the key ID that I could get from the signing key details available from the Kubernetes API. So how we build the URL for that case would be https and the bucket name .s3.region .amazon AWS. And remember, we are going to use a subpath within the bucket. So in my case, I'm going to use the first 8 characters of the key ID that I got from the Kubernetes cluster. This could be anything that identifies the cluster for you. Just for my case, I'm going to use the key ID in this cluster. Right, so that's the first flag that I wanted to change. The second and the third flag are about the signing keys. And usually in a fresh Kubernetes cluster, you don't really need to change these details because most probably you'd be using the same signing keys as the bootstrap time details. So in this case, I'm going to keep the service account key file and the service account signing key file the same values as they were. But in your case, if you had custom generated key files, you'd have to change those values to point to those actual key files. The final flag that we need to verify here is not in a default configuration. So we are going to have to add that into this configuration. This flag called the API audiences has the value that would be included in the audience claim in a JSON Web Token that would be issued by the API server. I think the default value for this is going to be something like Kubernetes, but in our case, we could input something like AWS STS. Right, so with all the values changed, let me save this file and wait until the API server restarts. Right, so the API server has come back online after I saved the changes into the manifest files. If you don't have a kubedm setup, this could be a manual restart for the API server. But in my case, the API server container runs as a static pod managed by the kubelet itself. So I just had to save the manifest file for the API server to be restarted. So we can see the API server has been running for a minute now, so there are no issues to be found. All the changes we have included in the configuration should be reflected if we curl the well-known endpoints again. So I'm going to start the Kubernetes proxy again so that I could hit the HTTP API without having to specify all the MTLS details. And now we can see that the issuer URL has been changed to the S3 URL that I specified as the issuer URL in the API server. So let me get this and the signing key details out of the API and store them in files so that I could change certain values to reflect the S3 bucket details that we are going to have. Right, so I have extracted the OpenID discovery specification details out of the Kubernetes API server, but there is one detail that I need to change here where it still points to the Kubernetes server as the signing key URL. Now I need this to change so that it points to the same URL as the issuer. So I'm going to change this detail in the file itself. So after this change is done, both the issuer and the signing key URLs will point to the S3 bucket that we'll be using to store these files so that AWS can read them during Federated Identity Provider registration. Right, so I have the 2 files ready here. Now it's just a matter of uploading these files to the correct paths inside the S3 bucket. I already have a specific path inside the S3 bucket, but before I upload these 2 files into this endpoint, I have to create the same URL structure that was there in the Kubernetes API server in this S3 bucket. Right, so inside the URL /openid/v1, there should be a file called jwks. And inside well-known, we should have the OpenID configuration. So just to double check, we have the OpenID configuration inside well-known. And in this file, it has the issuer URL pointing to the S3 bucket and also the JWT signing key URL that is also pointing to the same bucket. So if we go inside the S3 bucket, OpenID v1, we should be getting the public key signing details inside this v1 folder. So this isn't even the end of uploading files into the S3 bucket. We have to expose these files so that AWS can reach this endpoint publicly and read the files. By default, the S3 bucket policies will not allow that. So we need to expose these files with an explicit bucket policy. So at this point, I have the block public access policy set to block any new bucket policy statements that would allow public access into any of the objects. So I need to turn this off. I have been using this bucket to test certain configurations in the past. So I have certain configuration that has already exposed certain details to the outside world. So I'm just going to disable this because we need to add a bucket policy statement that would expose our objects into public access. And I'm going to edit this existing policy that says allow access into these specific files, where I'd be using my own value. So at the end of the day, I'm granting public access or access to any party that is unauthenticated to these two specific files. Just to check off the security side of this, we are not allowing public access to any of the prefixes. We are not granting an umbrella policy that would allow public access in this case. We are being really specific. Any public access would be for specific files. Right, so if I test access to this file, we can see that we can access the file publicly without having to authenticate into AWS directly. So after adding the policy, I'm just going to go back and close the door in a sense so that no new policies would be able to grant public access into the objects. It's just me scratching my security side of things. It's a really good practice to always close as many doors as possible when you're going through places like this. Right, so if I go back to my architecture diagram, we are still at this place where we are trying to extract the details from the Kubernetes API into the S3 bucket. We have just exposed the details from the S3 bucket. The next step would be to register that place as a federated identity provider in AWS IAM. So to register a federated identity provider, I'm going to go into IAM dashboard, and in identity providers, I'm going to add a new provider. And in this, I'm going to select OpenID Connect because the specification that Kubernetes pretends to implement here is OIDC or OpenID Connect. And for the provider URL, I'm going to give the same URL that I used for that service account issuer flag. Just make sure that you use the exact value that you used for the issuer URL. Even if you miss this trailing slash, for example, AWS will not be able to match the issuer claim that would be provided by the JWT to this provider registration. And here I'm going to specify the audience that would be in an incoming JWT, and if we don't override that value with something else, that is going to be AWS STS, which we specified in the API server. So the provider is now registered, and we have just completed the step from here to here. This was just step 1. We have 2 more steps to go through to get an actual IRSA deployment. Alright, so this is a good place to wrap this video up. Please keep a lookout on the channel for the other videos. If this content was helpful, please like the video. If you haven't subscribed already, please subscribe. That interaction helps the channel a lot. And also you'll be getting notified when other videos come out. That's it for me for now. Thank you so much for watching. I'll see you in the next video.